collision model or collision theory as well. I think it fits well in the beginning so that you understand why reactions occur at all at different rates. So we're going to study reaction rates. From that, we get into rate laws by either the method of initial rates or integrated rate law, and then we cover mechanisms. So kinetics was a pretty good chapter for you. It's small, it's all tied together, so I think it's one of the more compact chapters. It doesn't sprawl all over the place like some of them do.
During a chemical reaction, reactants come together. Some bonds break while others form, and new substances are produced. Chemical reactions may proceed rapidly or slowly, depending on various factors such as temperature and reactant concentration. Collision theory is a model that explains reaction rates. The fundamental assumption is that reactions occur when reactant particles collide. Because increasing reactant concentration increases the collision frequency, it also increases the reaction rate. However, not all collisions between A2 and B2 molecules are effective in forming products. In many collisions, the reactants don't collide in the right way. An effective collision is one in which molecules collide with proper orientation and with sufficient energy to break bonds. The minimum energy colliding molecules must have in order to react is called the activation energy. Collisions with less than the activation energy do not form products. Only those collisions with energies greater than the activation energy can rearrange to form the transition state and go on to become products. When the temperature is raised, the average kinetic energy of the molecules increases. As a result, a greater percentage of collisions have energies greater than the activation energy. Therefore, the reaction rate increases as a function of temperature. Perhaps you have heard of catalysts speeding up a reaction. Catalysts perform this feat usually by reducing the activation energy needed to form products.
So we're going to go into a little more detail about all of those factors that affect the collisions. So we know that in order for reactions to occur, molecules must collide with enough energy and the correct orientation. Only a small number of collisions will produce reactions because only the effective collisions can cause a reaction. Not all of your collisions are effective. They don't have those two components of enough energy and the right orientation. So the collision energy must equal or exceed the activation energy, and the orientation must allow for bonds to break and new bonds to form. So as you're going up the energy barrier, you need to make sure that you have enough energy to break those bonds, and then when you're coming down on the other side, you have to be able to reform those bonds. So collision energy needs to have enough activation energy, and you need to be able to form those new bonds.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2. For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting. If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
So activation energy is that minimum energy, that energy barrier that you need to get over to get those products to turn into reactants. You may also hear it called a transition state or activated complex. That's the species that's formed at the peak of that activation energy hump. It's not a product, it's not a reactant. These bonds are breaking, and these bonds over here are forming. So again, the transition state is breaking bonds and forming bonds. If you can't get over that energy barrier, you cannot get those products to form.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
So you want to make sure you're clear that this activated complex or transition state is the highest energy state that you will get to, whether you end up being exothermic or whether you end up being endothermic. You still have your most unstable state being your activated complex or transition state. So again, here is bonds stretching and breaking and bonds forming. Over here, your reactants have more energy than your products, so you are exothermic, but you still had to get over that energy barrier. Here, your reaction is endothermic, okay, but you still had to get over that energy barrier. The lab that we did, the first lab that we did with kinetics, and I believe we did only two. We did this one and the fading of the crystal violet dye with the colorimeter, but this one was a lot more fun, where we had the blinking iodine clock reaction, and we looked at concentration and temperature and a catalyst. So if you remember, we mixed our reactants. This is probably an increase in the concentration of one of them. And there's a blinking of that, and there's Ashton's sweet smiling face. What you're looking at is that the reaction is going through some mechanism steps that we can't see until that final slow step, which controls the entire reaction, kicks in. So that comes back when we learn about mechanisms. So your temperature affects your rate because your higher temperature has faster moving molecules. That's basic kinetic molecular theory. That means it has more frequent and higher energy collisions. Again, think about your gas laws. Think about basic kinetic energy. So more of your molecules at that higher temperature have the needed activation energy. If this is the activation energy here, then as you have this higher temperature, more of the molecules have that necessary activation energy, where down here, only these molecules have that necessary activation energy. So temperature gives you higher, faster, more frequent, and higher energy collisions, and more molecules have the needed activation energy. All of this increases your rate. Increasing temperature always increases your rate. So a high temperature has a much larger number of molecules, the area under that curve, that have that necessary energy. These are Boltzmann's distributions. I'll go back for a second if I want to reinforce. Your Boltzmann's distribution will always show, so if you have a number of molecules over here and your kinetic energy here, so when we get into heat, we come back to this discussion of kinetic energy and temperature. But right here at the peak of the curve, that's where most of your molecules have their energy. That's the average kinetic energy. Most of the molecules have that. At your higher temperature, that curve broadens and flattens so that you have more molecules having a greater amount of kinetic energy. Energy barrier, T2, more molecules have that necessary energy. So if we look at this demonstration of the hydrogen explosion, the second reaction probably just did not have enough activation energy to get the hydrogen, ignited it, but it didn't have enough to give it that nice explosion. The reaction still probably took place. Clearly we can see the hydrogen spewing out, but it did not give us that fast reaction rate. The reaction was the same, the rate was different. So, concentration is one of the most common things that we use to change our rate. If we have 1 molar HCl, we know it's going to react slower than 6 molar. 6 molar has more molecules, you have more collisions. If you have more collision frequency, then you're going to have a faster reaction because more of your molecules will be effective. You don't get all of them to be effective, but if you increase your collision frequency, then you will have more of those collisions, so more of them may be effective. Your particle size, since molecules only collide at the surface, if you have solids, smaller particles will give you a greater surface area and a faster reaction. This is a substance that will burn slightly when you hit it with the burner flame, but if you blow it through air and increase that surface area, you are increasing the ability of oxygen to react in a greater, since you've got all this surface area, and a much faster reaction. So the difference between iron rusting slowly and putting iron in a 100% oxygen environment and taking the iron and powdering it and increasing the temperature, both in this scenario, will give you a faster reaction. Your final delta H would be exactly the same. The change in heat would not be different. This would just occur faster, and this would be over time. Catalysts do something completely different. They change the entire mechanism. They change the slow step so that it requires less activation energy. So when we talk about catalysts at the end, we're looking at changing the mechanism. So we'll come back to catalysts when we get to mechanisms in other sections. So a catalyst does lower the activation